Hello, everyone. Here we are at the start of week 2 of 6 for Earth Science, SCI 110. Tonight I'm going to talk a little bit about the overlook of life here on Earth, over the life of the Earth, which we date to about 4.5 billion years. And then we'll look at the fossil record. And then a little later on, we'll have a kind of a lab where you'll have some questions to answer, and that'll be this week's assignment. But I'll put all of that on Blackboard for you. All right, so as we look at the, origin of the Earth, right, we're looking at about 4.6 billion years ago, and that's when that first nebular hypothesis, came about. And then it took about 1 billion years to about 3.6 billion years ago till we began to see the first single-celled life here on Earth, which we now know to be bacteria. And it was the bacteria that we can thank for adding the oxygen to the atmosphere, which, as we know from last week, was predominantly helium and hydrogen. And we, get into different eras, and you can see it's only been 65 million years that mammals have been here on the Earth. Those are the oldest fossilized remains that we've managed to find. You can see much older, of course, fish, plants, reptiles, amphibians. And then it's only been about 300,000 years that the first humanoids, our most recent relatives, have been here on Earth. So, how do we, prove this? Well, we prove this through what we call the fossil record. We know there's lots of different fossils, right? In addition to imprints, like you see right here, there are bones, teeth, other molds and casts. There could be things caught in amber and preserved in a liquid called amber, which is very much like, you look at the Jurassic Park, the mosquito was in the amber. That's a fossil. So hair could be a fossil. So anything that doesn't get broken down over long periods of time. So as I said, fossils can be a lot of different things: impressions, petrified rock, molds, casts, all those things, teeth, like you see down here. All of those things can be fossils. But what they have in common is a very sudden and quick burial, usually in sediment that hardens over time. And that's where we get our sedimentary rock from. We'll take a look at the rock cycle next week. But there's a lot of different things that are fossils, but they're all formed really the same way, right? Through great pressure of sediment and being buried. There's some other, looks. This is a trilobite, which is one of the most common fossils that we have. Some marine animal, but here's a mold and a cast, right? The mold over here, the cast, the kind of negative opposite, I guess, of the mold. Imprints, petrified wood, all of these things would be considered to be fossils, right? And that's what we would consider to be direct evidence, things that we have concrete evidence of. Now, this direct evidence, here's the amber with the mosquito inside of it. Amber is kind of a hardened sap that comes from trees, and as it oozes out of the tree, it would trap certain insects. Certain areas of the world, Lithuania, for example, is one place where you see a lot of amber. So much so that there's a lot of jewelry that is made from amber. Here's more of a imprint. This black color indicates the carbon that was in the tissue of this particular fern-like plant. So fossils are good sources of historical evidence. Here's a footprint that would be fossilized remain, any type of tracks, burrows, for example, that are made in rock, wood, any sedimentary rock. Those are all considered fossils. Coprolites are fossilized dung or the content of the stomach. Again, that wouldn't have been broken down over time. Gastroliths are really an interesting, what we consider to be fossil. They're basically stones that reptiles would ingest in order to aid in digestion, right? Those stones would rub up against because the dinosaurs and things would eat large amounts of plants. So the gastroliths aided in the breakdown of food particles. Kind of an interesting fossil. When we're talking about dating things, a couple different ways that we date. When we're talking about relative dating, we're talking about actual age, right? How many thousands of years or hundreds of years? My relative dating, would be my actual age. You can only say a rock is either younger or older. It's kind of relative. Absolute dating gives you much more of a pinpoint, right, on an actual age. And we use we call radioactive elements like uranium, for example, that deal in what we call half-lives. How long does it take half of an element to break down? And this kind of gives you a more precise, accurate dating. So relative dating, absolute dating, exactly the way they sound. Relative, we'll get you in a certain area. Absolute is much more of a pinpointing. Now, when we're looking at fossils as far as age goes, sometimes we use what's called the law of superposition, right? Where exactly was this fossil found? And of course, the further down a mountain or a body of rock that a fossil is found, the older it is, right? Because this fossil gets sediment on it, and then we have new fossils, and they get sediment on them, and then next group of fossils, they get sediment on it, and so on. So the youngest fossils will be found near the top of the mountain, and the oldest at the bottom. If you've ever been to the Grand Canyon, that's kind of a good example of what we call striated rock, where you can actually see the layers of rock. And in each of those layers are older and older fossils as you go from top to bottom. Now, when we're also talking about dating, we also go by not only the law of superposition, but the principle of original horizontality, right? Horizontal is going left to right here. Things are deposited horizontally, right? Now, if you see rock layers that are not horizontal like this, right? You can see these layers are, they're horizontal and they become vertical, horizontal and then vertical, up and down. That means that they had to have been moved, right? Something moved this particular rock along usually a plate, and this is what is involved in what we call mountain building, which we'll look at when we look at the rock cycle. But what happens is, continents or rock come together, and when they come together and hit, they push upward, and that's exactly what's happening right here. Another principle is what we call cross-cutting. So sometimes you'll see rock layers that don't belong in a particular area. So here's our youngest and our oldest layers, just like we said, right? Eldest at the bottom. And sometimes we'll have a intrusion that moves through all layers of that rock, right? So this happens to all be the same age, even though we're seeing it at different layers. Faults, which of course are cracks in the earth, usually are the result of seeing this type of intrusion, we call it dike, here in the rock layer. So, we try and match these up, right? And that's one of the reasons we know that the continents at one point were all together, right? Because of the fossils that we find that are separated by oceans, and we can match up the rock layers as having been together at one point. There's some more. You can see these striations very nicely here. You can see that they're, right, vertical, not just horizontal the way they should be, but they are becoming vertical, which is what we find whenever you'll see some of the mountain ranges, because continents come together, and in the movement, then it forces the rock up toward the surface. Sometimes we see what are called disconformities, right? This is kind of an intrusion that's not parallel to the Earth. So we see a lot of different types of movement moving here. Sometimes you'll see this underwater because of the movement of the water. We get different layers of sediment that get deposited. So we see a lot of, we don't see the striations the way we do sometimes in sedimentary rock when it's under the water. Angles, we will see, that's another piece here. Instead of just horizontal like this, we start to see the different angles and tilts that the rock layers give us. And here is kind of a drawing, and then here you can see it in actual life. Here's that parallel striations. With absolute dating, again, I mentioned earlier the half-life, how long does it take for half of something to decay away? And that's usually what we use for absolute dating. Now you see that uranium, the half-life is 4.6 billion years. So if you had uranium-238, it would take 4.6 billion years, right, for that 50% of it to decay away, which means, of course, that the other 50% is still left, and that is what has formed the element lead for us. So absolute dating gives us much more clear of as far as timing goes in the geological history of the Earth when something may have been. That's why radioactivity has such a long half-life. They say, like Chernobyl, for example, say that the city of Chernobyl will probably, as a half, that the uranium and plutonium that people were exposed to has a half-life of 20,000 years. So that city will be uninhabitable for that long a period of time. So that's kind of the fossil record, and we're going to start this week by looking at that. And then next week we'll start looking at the rock cycle. And then we'll move into plate tectonics, week 4, and then probably earthquakes, week 5, and then we'll probably pull it all together with some of the other weather-related anomalies, week 6, and then we'll be done at that point. So if you need anything, just please give me a call or drop me an email at Roosevelt, and I'd be happy to help you in any way I can. So that's it for our assignment for week 2. Hope you all have a good week, and it'll just be the one assignment, which is going to be a look at the fossil record for this week. And I'll put that up right now. And as with everything, we try for a deadline of every Sunday at noon. So a week from today at noon. That's it. Thanks, everyone.